Ancient builders performed feats of precision that seemed to defy logic. They aligned pyramids to the stars and paved roads straight across continents, all without lasers, satellites, or digital calculators. This video will reveal the ingenious system of simple tools and profound knowledge that made it all possible. How did a civilization with ropes and wooden poles measure the world with such stunning accuracy? By the end, you will understand the exact methods that turned grand visions into stone and mortar, solving a historical puzzle that reshapes our view of the past. We will start with the human body itself as a measuring device and journey through the clever instruments and celestial secrets that guided these masters of measurement. What does true ingenuity look like when you have nothing but the world around you? Precision for an ancient surveyor was not about fractions of an inch, but about achieving a perfect relationship between the human world and the larger order of the cosmos. It meant laying out a city grid where every street met at a perfect right angle, ensuring that water from a single canal could flow evenly to every field in a vast agricultural plain. It meant orienting a temple so precisely that on the dawn of a sacred day, the rising sun would flood directly through the main gate, illuminating the inner altar. These were not abstract artistic choices, they were functional and spiritual necessities. Leave half a city thirsty. A crooked property line could spark generations of dispute, and a temple facing the wrong star was seen as an offense to the gods. The challenge was monumental, literally. They had to take a small, carefully drawn plan scratched into clay or parchment and scale it up across a rugged landscape, translating delicate lines into foundations for walls that would stand for millennia. Every step of this process, from establishing a true north to maintaining a level plain over miles, had to be solved with nothing more than shadow, rope, and water. Their success is what we still walk among today, the ghost of their meticulous calculations made permanent in stone. Before any tool was crafted, the most reliable instrument was already at hand. The human body became the original blueprint for measuring the world. Your own forearm, from elbow to fingertip, defined the cubit, the length of a foot, the distance of a single stride, the span of your outstretched arms, a fathom. These were not rough estimates but the foundational units of an entire system. They were always available, universally understood, and intimately scaled to human work. A builder could walk off the length of a foundation trench by counting his paces. A rope could be knotted at intervals of a cubit, and an entire workforce could share a common language of dimension without needing complex conversion tables. But a moment's thought reveals the flaw. My forearm is not the same length as yours. A master builder, therefore, did not rely on just any arm. He maintained his own personal standard, a meticulously carved rod representing his official cubit, perhaps kept in a special case and treated with great reverence. On grand royal projects, this concept was scaled up to the ultimate authority, the royal cubit rod, an artifact of stone or precious metal that became the law of the land for every temple, pyramid, and palace. Every measuring cord in the kingdom was checked against this single, indisputable standard. The system's genius was in how it managed this inherent variability. Apprentices spent years not just learning to cut stone, but to replicate measurements with flawless consistency, training their eyes and hands until their personal cubit became a living copy of the master's rod. This relentless focus on replication turned a potentially chaotic system into one of remarkable precision. It established the first, crucial baseline, a shared reality of length and proportion from which all the greater complexities of surveying could begin. With a standard unit of length established, the next challenge was to carry that measurement across the open earth. This is where the humble rope transformed from a simple cord into a precision instrument. Crafted from braided flax or hemp, soaked in resin for durability and stretched to eliminate slack, these measuring cords were the ancient world's survey chains. Their true power, however, lay in the knots. A master rope maker would tie knots at precise intervals, perhaps every royal cubit, turning a length of fiber into a giant ruler that could be laid across a field or along the line of a future city wall. The professionals who wielded these tools, known in ancient Egypt as rope stretchers, were held in high esteem. Their title, harpadonapti, literally means those who tie knots, but their work was the bedrock of geometry. A team would drive a stake into the ground, stretch the knotted rope taut to its full length, and plant another stake, repeating this process to measure out vast distances with remarkable consistency. But their most brilliant trick was creating perfect right angles, the essential cornerstone for any rectangular building or aligned street grid. They did not need a complex brass square. Instead, they used a single rope with exactly 12 evenly spaced knots. By having 3 team members hold the rope taut at the 3rd knot, the 7th knot, and the 12th knot, they formed a triangle with sides of 3, 4, and 5 units. This specific ratio, a Pythagorean triple long before it had that name, guarantees a perfect 90-degree angle between the 3-unit and 4-unit sides. One rope stretcher would stand at the corner point, another would sight down the 3-knot leg to set one wall line, and a third would confirm the 4-knot leg for the perpendicular wall. In a matter of moments, using nothing but a knotted cord and practiced teamwork, they could establish the flawless right angle upon which an entire temple's orientation depended. This was not abstract mathematics, it was applied physics made visible in fiber and tension, a perfect marriage of simple materials and profound understanding that turned geometry into stone. But a knotted rope, for all its genius, was a tool of the earth, best suited for laying out the foundations of a single building. To impose order across an entire empire, the Romans required something more, an instrument that could project lines of sight with unflinching authority over miles of open countryside. Their solution was deceptively simple, a device called the Groma. Picture a tall wooden staff planted firmly in the ground. At its top, a horizontal crossarm pivoted freely, and from each of its 4 ends, a perfectly weighted plumb bob hung on a thin cord. The surveyor, known as an agrimensor, would first use the plumb lines to ensure the central staff was perfectly vertical. Then, by sighting along pairs of opposing cords, he could establish a flawlessly straight line in any direction he chose. To create the famous right-angled grid of a Roman military camp or a new agricultural colony, he would sight one line, then simply rotate the crossarm 90 degrees and sight the perpendicular. The suspended bobs, swaying gently in the breeze, gave a constant, visible reference to gravity's true vertical, translating the abstract concept of a straight line into a physical guide that could be followed by teams of laborers stretching chains and driving stakes far into the distance. This was the instrument that carved the straight, relentless lines of Roman roads across hills and valleys, and that divided vast conquered territories into the orderly squares of centuriation, the grid system of land allotment for veterans. With a Groma planted at a central point, the entire landscape could be organized into a precise chessboard of property lines and irrigation ditches, a geometric dream made real through the steady alignment of 4 dangling weights. It turned the surveyor from a measurer into a creator of axes, defining the very skeleton upon which the muscular infrastructure of the empire was built. Yet even the straightest road or the most perfectly squared building foundation would be useless if it did not respect the unyielding law of gravity's pull. For the grandest and most vital of ancient engineering projects, the aqueduct, a true horizontal plane, was not a matter of convenience. It was the absolute difference between success and catastrophic failure. Water does not flow uphill. To deliver life-giving water from a distant mountain spring to a thirsty city 50 miles away, the channel must maintain an exquisitely gentle, constant downhill slope, often as little as a few inches of drop for every mile of length. A single undetected hump would create a dam, a hidden dip would cause destructive turbulence. The surveyors tasked with plotting this path across rolling hills and shallow valleys needed an instrument capable of seeing the invisible, a tool to reveal the true level of the earth itself. Their masterpiece was the Corobates. Picture a wooden bench as long as two men lying end to end, perhaps 20 feet in length, mounted on sturdy legs. Along the top of this bench ran two perfectly parallel channels, carved into the wood and filled with water. The principle was elegantly simple, yet devastatingly accurate. Water, when undisturbed, always finds its own level. By sighting along the surface of the water in these twin channels, or by using a small sighting rule mounted on the bench, an operator could determine a perfectly horizontal line of sight. The survey crew would set up the Corobates at one point and peer along its established level to a graduated rod held by an assistant some distance away. By reading the mark on the rod, they could calculate the precise difference in height between their position and the next. They would then move the instrument forward, leapfrogging across the landscape, building up a meticulous profile of the terrain inch by painstaking inch. To ensure the Corobates itself was perfectly level before taking a sighting, the engineers had a clever backup. If the wind was too strong, rippling the water in the channels and making a sighting difficult, they could use a simple plumb line hung from the center of the bench. By checking the alignment of the line against marked grooves on the legs, they could achieve the same perfect setup. This relentless, incremental process is how they charted the miraculous paths of Roman aqueducts, maintaining that vital, gentle gradient for distances that stagger the modern mind. For smaller, more localized projects, like ensuring the floor of a bathhouse drained properly or checking the level of a foundation trench, a simpler tool sufficed. This was the libella, essentially a wooden frame with a plumb line hanging from its peak. When the plumb line aligned with a mark at the frame's center, the 2 feet resting on the ground were level. It was quick, portable, and perfect for the job at hand. The Corobates, however, was the instrument of grand ambition. It translated the silent, patient truth of still water into a language of actionable data, allowing human minds to outwit geography and command gravity itself to serve the city. With its long sight line, it could average out minor bumps and hollows in the ground, seeing the larger trend that a shorter tool would miss. It was this patient, step-by-step conquest of elevation that made the impossible flow of water across vast distances a mundane reality of Roman life, a testament to the power of observing a simple natural principle with unwavering precision. But even the longest sight line from a Groma eventually faded into the blur of distance. To carve a road straight as an arrow for 50 miles, or to align a ceremonial avenue directly with a mountain peak on the horizon, ancient surveyors had to master a technique of pure vision and coordination. They moved from using a single instrument to orchestrating a human chain of observation, a process known as ranging. It began with 2 master surveyors standing at the intended start and end points of the line, perhaps a hilltop shrine and a distant river ford. Each held a tall, slender marker pole. The trick was to get every point in between to vanish. A third surveyor, somewhere in the middle valley, would plant his own pole and then move it left or right based on shouted or signaled commands from the masters at the ends. He would shift it until, from the perspective of the master at the starting point, his pole perfectly eclipsed the one at the far destination. At that precise moment, his pole ceased to be a separate object. It became a dot on an imaginary straight line stretching across the landscape. He would then drive his stake firmly into the ground, marking one verified point on the true path. The team would then repeat this process, leapfrogging forward, using each newly set stake as a fresh reference point to guide the next. Over rolling hills or through light woodland, they created a dotted line of stakes across the earth, a temporary constellation that mapped an unwavering geometric idea onto the messy reality of the terrain. For even greater distances or across wide bodies of water, visibility itself became the challenge. On a clear, windless day, a column of smoke from a carefully tended fire could serve as a towering, temporary marker, visible for many miles. At night, the steady glow of a beacon flame could anchor the line. This was surveying at its most elemental, a conversation conducted across vast spaces with poles, fire, and human eyesight. It required immense patience and flawless communication, turning a team of individuals into a single, distributed measuring device. Every straight Roman road that seems to defy the natural curves of the land began with this patient, step-by-step dance of alignment, a testament to the power of coordinated sight long before the invention of the telescope. Yet the most permanent and unchanging map for these ancient masters was not on the earth, but painted across the night sky. To align a monument for eternity, they looked beyond the shifting hills and turned to the celestial clockwork, using the sun and stars to anchor their creations to the cosmos itself. The most fundamental task was finding true north, and one of the simplest methods relied on the sun's predictable path. A surveyor would plant a vertical pole called a gnomon into level ground. As the sun moved from east to west, the pole's shadow would sweep in a long arc. The trick was to mark the tip of that shadow at different points throughout the day, creating a curve of dots on the earth. By drawing a smooth arc through those points, then bisecting the narrow angle between the arc and a circle drawn around the pole, they could identify a perfect east-west line. This was especially precise during the equinoxes, when day and night are of equal length, as the shadow path becomes a nearly straight line. With east and west firmly established, finding north and south was a simple matter of drawing a perpendicular. This solar method was elegant and accessible, a direct conversation with our closest star, but for the ultimate in precision, especially for a project intended to stand for ages, the sun had a limitation. Its path changes slightly with the seasons. The stars, however, offered a fixed and unwavering reference. They would turn to the circumpolar stars, those that never dip below the horizon, but instead rotate around the celestial North Pole. An Egyptian surveyor working on the foundation of the Great Pyramid over 4,000 years ago might have used a pair of simple sighting tools, perhaps notched rods or aligned walls of a preliminary trench. By observing two stars that circled the pole, like Kochab and Mizar in the bowl of what we call the Little Dipper, they could pinpoint true north with astonishing accuracy. They would wait for the moment when both stars appeared to align vertically, one directly above the other. A plumb line hung between the surveyor's sighting instruments would then define a perfect meridian line, a north-south axis drawn from the heavens down to the desert floor. It is this stellar technique that likely explains the breathtaking alignment of the Great Pyramid. Its sides are oriented to the cardinal directions with an error of less than 1/15th of a single degree, a deviation so minute it rivals what modern engineers might achieve. This was not guesswork, it was a calculated, patient act of celestial navigation. The pyramid does not just point north, it is locked to the very axis of the sky, a terrestrial mountain mirroring the eternal turn of the stars. In this way, the surveyors merged the earthly and the divine, using the immutable laws of the cosmos to create a monument that would itself become a permanent fixture, a human-made North Star set in stone. But the relentless ambition of ancient engineers soon demanded even more from their instruments. To conquer the most unforgiving terrain, they needed a device that could measure not just straight lines and level plains, but the precise angles between them. The answer was the Dioptra, a sophisticated sighting tool that stands as the direct ancestor of the modern theodolite. Picture a circular bronze plate, carefully engraved with 360 degrees, mounted on a sturdy tripod. Across this disc, a ruler with raised sighting pins at each end, called an alidade, could rotate freely. By peering through these pins to line up a distant target, an operator could read the exact horizontal angle from a fixed reference point. Later, more advanced versions incorporated a second, vertical circle, allowing the Dioptra to measure slopes and elevations with equal precision. This single instrument could perform the combined functions of a Groma for alignment and a Corobates for leveling, but with a far greater degree of accuracy and flexibility. Its power is best illustrated by one of history's most daring engineering projects, the Tunnel of Eupalinos on the Greek island of Samos, constructed in the 6th century before the Common Era. The task was to carve a conduit over 1,000 meters long straight through the heart of a mountain to bring fresh water to the city. The risk of miscalculation was immense. Two teams starting from opposite sides of the mountain would dig toward each other. If their headings were off by even a small fraction of a degree, they would miss each other entirely, wasting years of labor and leaving a useless crooked passage in the rock. Historians strongly believe the engineer Eupalinos employed a Dioptra to solve this problem. From the starting point on each side, his surveyors would have used the instrument to meticulously map a series of staggered marker points down the mountain slopes and across the ridges above the intended tunnel path. By taking repeated angular measurements from these high vantage points, they could calculate the correct line through the unseen interior of the mountain. It was a three-dimensional puzzle solved with geometry and light. When the two digging teams finally met in the middle, the alignment was nearly perfect, with only a slight, deliberate offset in the central section to account for a minor surveying correction. This was not luck, it was the triumph of angular measurement. Beyond such heroic tunneling projects, the Dioptra became the ultimate tool for mapping the world itself. A surveyor could set up the instrument at a known high point, and by measuring the angles to prominent landmarks, distant mountain peaks, or the corners of a vast estate, create an accurate scaled diagram of the terrain. It allowed for the calculation of inaccessible distances, like the width of a river or the height of a wall, using principles of trigonometry. This ability to capture the world in a network of angles and triangles represented the pinnacle of ancient optical surveying. It moved beyond marking the land to truly understanding its form, transforming the rugged, unpredictable Earth into a set of solvable geometric problems. The Dioptra's rotating sight bridged the gap between the earthly and the conceptual, giving engineers the confidence to plan projects that dared to defy the very shape of the landscape. The silent truth of still water offered more than just a sight line on a Corobates. In the hands of ancient builders, water became a tangible, self-leveling medium that could be scaled to any project, from a single house to an entire city. For establishing a perfectly flat foundation bed across a wide area, perhaps for a temple platform or a massive granary floor, they employed a method of beautiful simplicity. Teams of laborers would dig a shallow grid of narrow trenches across the entire site, all interconnected like the lines on a piece of graph paper. Then they would carefully fill this network with water. Since water always seeks its own level, the surface inside every trench, from one corner of the site to the other, would rest at exactly the same height. All a foreman had to do was walk along these liquid rulers, using a simple marked stick to measure down from the water's surface to the ground at countless points. Where the ground was too high, workers would chip it away. Where it was too low, they would add fill material and compact it. They worked until the distance from the waterline to the earth was uniform everywhere. Once this was achieved, they could drain the trenches, confident that the entire prepared bed was a single, unbroken plane, ready to receive the first course of stone. This was leveling made physical and democratic, a standard that every worker on the site could see and understand without needing specialized instruments. But what happened when you needed to transfer that perfect level benchmark from one side of a rocky outcrop to the other, or from the valley floor up to a construction site on a hillside? You could not dig a continuous water trench through solid rock. The solution was another brilliant application of a basic principle, that of communicating vessels. Imagine a long, flexible tube made of leather or animal gut, carefully sealed to prevent leaks. If you fill this tube completely with water and hold both ends up, the water level inside each open end will settle at precisely the same height, regardless of the twisting path the tube takes in between. Ancient surveyors used this exact method. They would establish a known level point at a central location, perhaps using a marked post set in a still pool. Then a team of two would take the filled hose. One person would hold one end fixed at the reference water level, while the other could climb a slope, scramble over rubble, or even go around a corner, playing out the hose as they went. When the second person held their end up, the water inside would settle, and they could mark a new point on a stake or a wall at that exact height. In this way, the level could be transmitted or communicated across any obstacle that would break a line of sight, creating a network of elevation points all tied back to a single, authoritative source. This fundamental understanding of water's behavior empowered some of the most sophisticated hydraulic engineering in the ancient world. In the arid landscapes of the Persian Empire, engineers used networks of gently sloping underground canals called qanats to tap distant mountain aquifers and deliver water to cities and fields without a single drop lost to evaporation. Maintaining the precise, consistent downhill gradient for these tunnels, which could stretch for dozens of miles, relied on the very same leveling techniques, likely using water-filled trenches on the surface above to guide the diggers below. For the Romans, this principle was everywhere. It was in the public fountains that bubbled evenly in every district because the feeding reservoirs were leveled, and in the intricate floor heating systems of the great bathhouses, where hot air and water needed carefully graded channels to flow correctly. The simple, undeniable fact that water finds its level was not just a tool, it was a foundational law they built their world upon. It allowed them to think in three dimensions, to conquer elevation not with brute force, but with quiet observation, turning a humble element into the most reliable partner an engineer could have. Yet the most elegant instruments were useless without the master key to unlock their potential, the language of geometry itself. This was not the abstract geometry of a classroom, but a living, breathing knowledge of shapes and proportions, a practical toolkit carried in the mind of every master builder and surveyor. They understood that the world could be broken down into triangles and circles, and that by knowing a few simple rules, they could solve problems of distance, height, and area that seemed impossible to measure directly. The most powerful of these tools was the concept of similar triangles. Imagine a surveyor needing to know the height of a cliff face to plan a bridge abutment, or the width of a raging river to design a pontoon crossing. He could not simply walk over with a measuring rod. Instead, he would set up two stakes of known height in a straight line leading away from the obstacle. By sighting from the top of each stake to the top of the cliff or the far riverbank, he created two imaginary, overlapping triangles. Because the angles were the same, the triangles were similar, meaning their sides were in perfect proportion. He knew the exact distance between his two stakes and their heights. By measuring the distance from each stake to the point where his sight line hit the ground, he now had all the numbers he needed. A simple ratio, a cross multiplication, and the previously unknowable height or distance revealed itself. This was mathematics made manifest, a way of using a small, accessible triangle as a key to unlock the dimensions of a giant, inaccessible one. For calculating slopes like the consistent gradient of a road or an aqueduct channel, they relied on the foundational relationships within a right triangle, the very essence of basic trigonometry. They did not have sine and cosine tables, but they understood the unchanging ratios within specific, well-known triangles. The 3-4-5 triangle from the knotted rope was their most trusted companion, guaranteeing a perfect right angle. But they also knew the properties of other Pythagorean triples and understood that if you knew the length of one side of a right triangle and one of the angles, you could calculate everything else. They might use a simple graduated quadrant, a quarter circle of wood or bronze marked with degrees, to measure an angle of slope. Then, using known ratios for common angles or through geometric construction, they could determine how much a road should rise over a given horizontal run. This intellectual framework turned guesswork into calculation. It allowed a Roman engineer to confidently state that an aqueduct needed to fall precisely 1 meter for every kilometer of length to maintain the correct flow. It enabled a planner to take a small, detailed scale model of a city quarter, perhaps drawn on a wax tablet, and know exactly how many standard blocks would fit between the proposed forum and the river, converting a miniature vision into a full-scale reality. The tools gave them data, points and lines and angles, but it was this internalized, practical geometry that gave that data meaning, allowing them to weave isolated measurements into a coherent, buildable plan. It was the invisible blueprint that existed long before the first foundation stone was laid, the logical scaffold upon which all their physical ingenuity ultimately rested. But a master surveyor's perfect line, drawn in the dirt or sighted from a hilltop, was a fleeting moment. To transform that single act of precision into a monument that would rise over years, built by thousands of hands, required something more permanent than a memory. It demanded a shared vision that could be passed from person to person, from season to season, without distortion. The true anchor of ancient engineering was not just the tool in hand, but the plan on the page. Archaeologists have discovered scaled drawings on fragments of papyrus and clay, and full specifications carved directly into stone walls. These were not mere sketches, they were the legal and technical blueprints for the entire endeavor. A famous example comes from the tomb of the Egyptian architect Ka, where a papyrus roll was found depicting a scaled plan of a vaulted chapel, complete with written dimensions. The lines were precise, the proportions clear. This document allowed the architect's intent to survive his own presence on the site. It could be consulted by a foreman months or even years later to resolve a dispute about a wall's thickness or the placement of a column. For truly massive public works, standardization was enforced through written specification documents. A Roman contract for building an aqueduct might not just state the length, but would legally mandate the exact width and depth of the channel, the type of mortar to be used, and the slope to be maintained, often referencing a master plan held in the civic archives. This turned subjective quality into an enforceable measurement. Yet in a world before photocopiers, how did every foreman and stonemason work from the same invisible blueprint? The answer lay in a rigorous chain of command and a universal language of units. The royal cubit rod in Egypt or the Roman foot standard inscribed in a temple forum were the absolute authorities. Master builders would use these to create secondary standards, perhaps brass rods or marked wooden beams, which were entrusted to the lead foreman on each section of a project. These foremen, in turn, were responsible for ensuring that every measuring cord and template used by the laborers was checked and rechecked against that standard. Instructions flowed downward with crystalline clarity. The architect conveyed the overall plan and critical dimensions to a small group of senior master builders. Those masters broke the project into manageable sequences, translating the plan into specific tasks for each foreman, a daily tally of blocks to be cut to a certain size or a trench to be dug to a precise depth. The foreman's job was not to design, but to execute with unwavering fidelity to the measured instructions he received. He would use his standardized tools to mark the guidelines directly onto the stone or the ground, often with red ochre paint, creating a physical manifestation of the abstract plan for the work crew to follow. This system transformed a chaotic construction site into a coordinated machine. A laborer shaping a granite block in a quarry miles away could do so with confidence, knowing his cubit ruler was the same as the one being used by the mason fitting that block into a wall at the distant temple site. The written plan ensured continuity of vision, the standardized units ensured consistency of parts, and the clear hierarchy ensured that every action, from the architect's first calculation to the apprentice's final hammer stroke, contributed to a single, coherent whole. The silent stones we admire today are not just a testament to strength, but to a forgotten symphony of communication, where a whisper of measurement passed from a papyrus scroll through a chain of trusted hands until it echoed in the perfect alignment of 1,000,000 stones. This meticulous system of communication and measurement finds its ultimate expression in a single, staggering monument. The Great Pyramid of Giza stands not merely as a tomb, but as a permanent testament to ancient surveying's highest possible achievement. Its precision is not a myth, it is a measurable fact that continues to humble modern engineers. The pyramid's 4 sides are aligned to the 4 cardinal directions with an error of less than 1/15th of a single degree. To grasp what that means, picture the face of a giant clock. If true north were at 12 o'clock, the pyramid's alignment would be off by less than the distance between the minute marks. Over its vast base length of 230 meters, that tiny angular deviation translates to a physical misalignment of only about 2.5 centimeters at the corners. This is not the work of builders guessing with the sun at noon. This is the signature of a master surveyor using the fixed stars. As we discussed, the likely method involved sighting on a pair of circumpolar stars as they crossed the meridian, using plumb lines to transfer that celestial north-south axis directly onto the meticulously prepared desert plateau. But before a single stone could be laid to that impossible standard, the ground itself had to be made perfect. The pyramid's base is not just flat, it is level to within an astonishing 2 centimeters across its entire area. That is like laying a foundation for a skyscraper the size of 10 football fields and having it be as level as a modern billiard table. How did they achieve such uniform flatness across an area so vast? The evidence points to the ingenious use of water. Archaeologists believe the builders first carved the bedrock into a series of low, grid-like retaining walls, creating a giant, shallow basin. They then flooded this entire area, turning the site into a temporary, perfectly level lake. The surface of the water became their universal benchmark. Teams of workers could then methodically cut down any remaining high points of bedrock until the water just barely covered the entire floor, ensuring every spot was at exactly the same elevation. Once drained, they were left with a flawless plain of living rock, a canvas of absolute flatness upon which the first course of casing stones could be placed with unerring accuracy. The construction of the Great Pyramid represents the sublime synthesis of all the principles we have explored. It used celestial observation to lock the structure to the cosmos, water leveling to defy the imperfections of the earth, and a rigid hierarchy of standardized measurement to maintain that precision through decades of construction. It was not built with magic or alien technology, but with an exhaustive, disciplined application of simple tools and profound natural wisdom. The pyramid is the proof that when human ingenuity is directed by a clear vision and supported by an unbroken chain of exact communication, the results can truly touch the heavens. The legacy of that geometric precision can be traced across continents, etched into the very earth by the relentless straight lines of Roman roads. These were not meandering paths worn by time, but engineered arteries of empire, and their construction began not with a shovel, but with a surveyor's unwavering gaze. To lay a road straight from a mountain pass to a river crossing 50 miles away, the Roman agrimensor would first establish his line of sight using the trusted Groma. From a high vantage point, he and his team would begin the patient process of ranging, setting a series of marker poles across the landscape until they had defined an invisible but perfect line from origin to destination. This was the road's backbone, its intended path, but the true challenge came next, for the land itself was rarely so accommodating. The surveyor's genius lay in his commitment to the straight line as an ideal, not as a rigid, impractical rule. When his sight line met an impassable cliff or a swampy valley, he did not simply abandon the straight path. Instead, he would deviate only as much as absolutely necessary, creating a gentle curve or a short zigzag to navigate the obstacle, before immediately returning his markers to the original, unswerving alignment. This principle gave Roman roads their characteristic appearance on a map: long, ruler-straight segments connected by brief, purposeful angles, a testament to a surveyor holding a geometric truth against an unyielding world. Once the center line was established and approved, the real work of translation began. Using the Groma again, the team would mark parallel lines on either side, defining the road's full width, often a standardized 20 Roman feet for a main via. Every detail was measured and recorded, turning a vision into a set of instructions that could be followed by legionaries and laborers across the entire empire. To manage the equally critical element of slope, they employed their leveling tools, likely a simple form of Corobates or libella. A Roman road was not flat. It was expertly cambered, slightly higher in the center than at the edges to shed rainwater into drainage ditches. Maintaining a consistent, gentle gradient over long distances, especially when climbing hills, required meticulous incremental surveying. They would calculate the necessary rise, perhaps 1 foot for every 20 of horizontal travel, and check it constantly as the roadbed was built up, ensuring that neither man nor wagon would ever face an impossibly steep incline. This systematic approach was sealed into the landscape with milestones. These stone pillars were not mere signposts. They were the empire's official ledger, recording the exact distance from the road's starting point in the Roman Forum or a major provincial capital. Every 1,000 paces, a measured Roman mile, a new milestone was planted, its inscription declaring the authority of the emperor who built it and the precise distance to the next town. This created a universal, reproducible coordinate system. A traveler from Gaul could understand exactly where he was on a road in Syria because the language of measurement was identical. The straightness of a Roman road, therefore, was not an accident of stubbornness. It was the physical manifestation of a system, a reproducible method of sighting, leveling, and recording that could be taught to any competent engineer in any province. It reduced the need for individual genius by embedding genius into the process itself. The road did not rely on the memory of a single master surveyor. It relied on the Groma's plumb lines, the written specifications for width and gradient, and the immutable truth of the milestone's number. This is how they built not just roads, but a networked, measurable world, where geometry became the common language of control and connection, long before the first stone was ever laid. This breathtaking precision, however, existed within a world of very human limitations. The tools we have described were masterpieces of their time, but they were not infallible. Every single measurement contained a tiny, almost invisible margin of error. A knotted rope, no matter how carefully braided, could stretch a fraction with humidity or tension. The plumb lines of a Groma would sway in a gentle breeze, blurring the perfect sight line. A water surface in the channels of a Corobates could ripple from a distant footstep or a change in temperature. These were not mistakes, but inherent realities of working with natural materials. The true genius of ancient engineering lay not in eliminating these errors, which was impossible, but in understanding, managing, and designing around them. They worked with a sophisticated concept of tolerance. A master builder knew that over a distance of 100 cubits, his rope might be off by the width of a finger. Over 1,000 cubits, that small error could multiply, potentially throwing an alignment off by several hands' breadths. The solution was to break monumental projects down into smaller, manageable sections, each with its own local control points. Instead of measuring the entire side of a pyramid from one corner to the other in one go, they would establish the precise length for one course of stones at a time, constantly checking back to the primary celestial alignment. This compartmentalization contained error, preventing a small mistake at the beginning from growing into a catastrophe at the end. They also understood the behavior of their materials. Stone settles, mortar compresses, the ground itself shifts over seasons. Their designs often incorporated this knowledge. The slight inward slope of the pyramid's faces, for instance, is not an optical illusion but a structural feature that helps channel the enormous weight of the stones downward and inward, adding stability as the monument settled over its first years. The flexible joints in some Roman aqueducts allowed sections to shift slightly during earthquakes without the entire structure cracking. This was a philosophy of functional precision. The goal was not abstract mathematical perfection for its own sake, but a perfected function. Did the aqueduct deliver water without leaking or losing flow? Did the temple stand straight and true for generations? Did the road provide a stable, efficient route for travel? If the answer was yes, then the work was a success, even if every single measurement was not flawless to a microscopic degree. They judged their work by the enduring result, not by the theoretical purity of the process. This acceptance of practical tolerance is what separates a rigid, brittle system from a resilient, living one. It allowed for the human element, for the wind on the desert plateau and the tremor in a surveyor's hand, and still produced wonders that stand today. Their legacy is not one of impossible, machine-like accuracy, but of profound wisdom, knowing what truly mattered in the dialogue between an ideal plan and an imperfect world. The final, breathtaking precision we see today was rarely achieved in a single, flawless act. These master builders understood that their tools and their eyes could be deceived, so they embedded a relentless process of verification into every stage of their work. The initial line cited with a Groma was just a proposal, the first draft written on the landscape. Its truth had to be proven again and again through simple, redundant checks. The most common of these was the test for squareness. After using a knotted rope to establish a right angle for a building's corner, the team would not simply assume it was perfect. They would measure the lengths of all four sides, and then they would measure the diagonals. In a perfectly square or rectangular space, the diagonals must be exactly equal. This was a beautiful, built-in fail-safe. If one diagonal was even a hand's breadth longer than the other, it meant the corners were not true right angles, and the entire shape was a parallelogram, not a square. The error was immediately visible in the numbers. The crew would then make tiny adjustments to their corner stakes, nudging them inward or outward, re-measuring the sides and diagonals until both diagonal measurements matched perfectly. This iterative dance of measure, check, and correct was the heartbeat of the site. We can see evidence of this empirical refinement in the very monuments that seem so impossibly exact. At the Great Pyramid, the base is not a perfect square. The sides vary by a few centimeters in length. This is not a mistake, but almost certainly the result of the builder's own verification process. They likely established their initial square using the stellar north alignment and their standard cubit measures. Then, as they built up the courses, they continuously checked and possibly adjusted the growing structure, prioritizing the visual straightness of the rising edges and the perfect level of each new layer over rigid adherence to the initial base dimensions. The goal was the pyramid's ultimate form and stability, not slavish obedience to a single day's measurements. The same principle guided the builders of Roman aqueducts. The Corobates could ensure a level site over a few hundred feet, but over 50 miles, the cumulative effect of minuscule errors in each setup could become significant. The engineers compensated by incorporating settling tanks and flow regulators at regular intervals. These structures acted as checkpoints. If the water level in a tank was too high or too low compared to the design, it signaled a gradient issue in the preceding section. Maintenance crews could then inspect that channel, making small corrections to the mortar or the channel bed to restore the proper flow. This was a system designed for long-term correction, acknowledging that precision was not a static state but a condition to be maintained through observation and care. This practical, hands-on philosophy transformed surveying from a theoretical science into a living craft. The master builder did not just issue commands from a plan, he walked the site, his eyes constantly moving from the string line in the dirt to the horizon and back. He knew that the sun's position changed the length of shadows used for alignment, so he worked at the same time each day for critical sightings. He understood that a measuring cord stretched differently when wet, so he allowed for it. Every decision was informed by the feedback from the material world itself, a constant conversation between the ideal geometry in the mind and the stubborn reality of stone, rope, and earth. The monuments that survived are not the ones built without error, but the ones whose builders had the humility to check their work and the wisdom to refine it. Yet for all their brilliant tools and geometric rules, this system had a fragile, irreplaceable core, the master's own trained perception. The most perfect Dioptra was useless in the hands of someone who did not know how to steady their breath while sighting, or how to account for the sun's glare on a distant marker. This was a craft, not a science, and its lifeblood flowed through generations of apprenticeships. A young man entering a master builder's workshop would not be handed a Groma on his first day. He would spend years performing the most mundane tasks, mixing mortar, hauling sand, and holding the measuring rod for others. This was not wasted time, it was sensory immersion. He learned the weight and stretch of a wet rope, the way shadows sharpened at different times of day, the sound of a properly struck chisel. He was developing what craftsmen call the knowledge in the hands, a tactile, intuitive understanding of materials and tolerances that no manual could ever convey. Slowly, he would be trusted with more responsibility, perhaps tasked with checking the water level in a trench or aligning a simple foundation string. Under the watchful eye of the master, his own eye was being calibrated. He learned to spot a deviation of a finger's width across a distance of 50 paces, not by measuring, but by looking, by sensing the slight tension in a guideline or the almost imperceptible curve in a row of stakes. This cultivated judgment was the true safeguard against error. Formal tools gave a measurement, but the master's experienced eye could tell if that measurement felt right within the context of the whole site, the slope of the land, and the behavior of the materials that day. They accumulated a vast library of practical, local wisdom, tricks of the trade passed down as oral tradition. A surveyor in Egypt knew that the desert sand shifted with the temperature, so he would take his critical alignments in the cool, stable air of dawn. A Roman aqueduct engineer learned to read the vegetation along a hillside as a clue to hidden springs or unstable ground that could undermine his channel. This tacit knowledge, carried in memory and muscle, filled the gaps left by even the best instruments. It explained how a team could maintain consistency across a project that lasted longer than a single human lifetime. When the old master finally passed his personal cubit rod and his worn set of sighting pins to his chief apprentice, he was passing more than objects. He was transferring a way of seeing the world, a legacy of attention that turned simple tools into extensions of a disciplined mind. The stones themselves bear witness to this human continuity, their seamless joints and unwavering lines speaking of countless small corrections, made not because a calculation demanded it, but because a trained eye saw that it was necessary. The fall of Rome did not erase geometry from the European landscape. While the grand imperial machine that built aqueducts and paved continents fell silent, the meticulous knowledge of the surveyor did not vanish. It found refuge within the quiet, disciplined walls of the monastery. Here, in scriptoria across the continent, monks meticulously copied not only religious texts, but also the surviving works of Roman agrimensores, the land surveyors. These manuscripts preserved the geometric principles, the diagrams of right angles, and the methods for dividing land. This was not an academic exercise. Monasteries were vast economic enterprises, managing huge estates called granges that required precise organization to feed their communities and support their charitable works. The monastic surveyor, often a brother with a practical mind, used these inherited Roman techniques to lay out orderly fields, orchards, and fish ponds. He would employ a simple version of the Groma, likely a staff with a cross and plumb lines, to ensure his vineyard rows were straight and his irrigation ditches followed a true gradient. The goal was the same as it had been for the Romans: functional efficiency and fair division, but now in service to spiritual sustenance rather than imperial ambition. This continuity of practice ensured that the language of measured land survived the political chaos, kept alive by the rhythmic, seasonal needs of agriculture and community. This preserved knowledge would soon be directed upward toward the heavens. The great age of cathedral construction demanded a new kind of precision, one that married earthly geometry with divine aspiration. Building a structure meant to inspire awe and last for centuries required foundations that were perfectly square and walls that rose vertically for hundreds of feet. The master masons used the same fundamental tools: the plumb line for vertical truth and the water level for flat foundations, often poured into long wooden troughs to check the level of the bedrock across the entire footprint of the future cathedral. But a new challenge emerged: the precise alignment of the church itself. Traditionally, a church was oriented with its altar at the east end, toward Jerusalem and the rising sun. Determining true east, however, required more than watching a sunrise, as the sun's rising point shifts north and south with the seasons. For the most important churches, a more accurate method was needed. This is where an adaptation of ancient astronomy entered the mason's yard, the astrolabe. This intricate brass calculator, originally used by astronomers and navigators, could solve complex problems of celestial time and position. In the hands of a learned cleric or a master builder, it became a surveying instrument. By observing the altitude of the sun at noon or the position of a specific star like Polaris, the astrolabe could calculate the exact meridian line, true north-south. From that, true east-west could be established with unerring accuracy. The foundation trench for the cathedral's choir and high altar would then be dug along this sacred axis, locking the entire immense stone prayer into the cosmic order. It was a profound fusion, using a tool of stars to orient a house of faith, ensuring that the light of the equinox sunrise would flood down the nave in a blaze of symbolic glory. The cathedral itself, rising from its geometrically perfect plan, became a testament to applied surveying in 3 dimensions. The master mason's secret was the template, not a paper plan, but full-size wooden patterns for every arch, window, and vault rib. These templates were crafted with exquisite care in the lodge on the ground, using compasses, straightedges, and the immutable ratios of sacred geometry. Once perfected, they were carried up the scaffolding to guide the stonecutters high above. This system guaranteed that complex curves matched perfectly from one side of the building to the other, even when the work was done by different teams who could not see each other's progress. The true test of the builder's skill was the vault, where soaring stone met in space. To set the temporary wooden centering that would support the vault stones until the mortar set, they relied on carefully measured chord lines dropped from key points in the upper walls, creating a 3-dimensional web of guidelines in the empty air. The decline of empire-scale projects did not mean a loss of skill, but a transformation of purpose. The core principles of establishing a line, checking a level, and maintaining a standard were preserved in the monastic ledger and the mason's lodge. They were adapted from mapping roads for legions to aligning choirs for choirs, proving that the need for precision is a constant thread in human endeavor, forever finding new forms in which to express its quiet, essential power. Long before the pyramids or the Groma, the landscape itself was being measured with a different kind of ambition. Scattered across the hills and plains of ancient Europe are monuments of a scale that still defies easy explanation, the great stone circles and colossal earthworks of the Neolithic world. These sites, like Stonehenge on the Salisbury Plain or the massive circular henge at Avebury, present a unique puzzle for the history of surveying. Here, we step back into a time before written records, before metal tools, and into a realm of pure speculation guided by physical evidence. The challenges these builders faced were monumental in a raw, fundamental sense. They were not plotting city grids or aqueducts, but imposing vast geometric shapes, perfect circles, and long ceremonial avenues onto a wilderness using nothing but stone, bone, and wood. The precision we can measure in their surviving works suggests a system, but one that leaves no instruction manual behind. The most iconic form, the stone circle, presents the clearest geometric problem. How do you create a perfect circle hundreds of feet across using only Neolithic technology? The most plausible and elegantly simple theory involves the very first surveying tool, a length of rope. A central stake would be driven into the ground, then a long rope, perhaps made of braided leather or plant fiber, would be tied to that stake and stretched taut. A second person would walk in a wide arc around the center, keeping the rope tight, while a third followed behind, digging holes or placing markers at the rope's end. This rope and peg method is mechanically perfect, capable of generating a flawless circle limited only by the length of the cord and the flatness of the ground. At sites like Stonehenge, archaeologists have found evidence of such a construction process, with the remains of a circular ditch and bank that may have been laid out this way long before the giant sarsen stones were ever erected. But the circles are only part of the story. Many of these sites incorporate precise alignments to celestial events, most famously the summer solstice sunrise at Stonehenge. Establishing such a long sightline, potentially over a mile or more to a distant horizon notch, required a different kind of skill. It likely involved a process of patient, generational observation. Over decades, watchers would have marked the extreme northern and southern rising points of the sun or moon against the skyline, using wooden posts or natural features. Once these limiting points were known, calculating the midpoint to find due east or the solstice position became a matter of careful counting and marking on the ground, perhaps using a long alignment of posts to transfer that celestial direction from the horizon ridge down into the ceremonial center. The scale of some earthworks pushes the boundaries of what seems possible without a coordinated plan. The massive bank and ditch surrounding Avebury, for instance, forms a circle over 300 meters across, enclosing an area greater than modern city blocks. To lay out something of that scale with any semblance of symmetry, the builders likely used a system of progressive refinement. They may have begun with a large, rough circle established by pacing or with a very long rope. Then, teams working on different sections could have used a simpler version of the ranging technique, sighting across the interior to ensure the curve was consistent from all angles, adjusting their digging as they went. The absence of a central point in many henges suggests they were not drawn from a single center, but were perhaps laid out as a series of connected arcs, a community project where the final, majestic form emerged from the collaboration of many hands following a shared mental template. This is where we enter the realm of greatest uncertainty. Unlike the Roman aqueduct engineer whose tools and methods were documented, the Neolithic surveyor left no treatises. We have the colossal results, but not the daily journal. This forces a reliance on experimental archaeology, where researchers try to replicate the feats using only the materials and physics available at the time. These experiments show that the tasks, while Herculean, were within human capability given immense social organization and a deep, accumulated knowledge of the land and sky. The precision of these sites is not the crisp, bureaucratic precision of Rome. It is an organic, monumental precision, born from collective memory and a desire to harmonize human ritual with the fundamental cycles of the earth and cosmos. It speaks of a different kind of mastery, one less about conquering geography and more about weaving their place within it, using rope, sight, and stone to create a sacred geometry that would anchor their world for millennia. The quiet mastery of the rope and the plumb line, however, could only carry human ambition so far. As the world grew larger in the minds of explorers and mapmakers, a new demand arose, not just for straight lines on the ground, but for precise angles across vast, open seas and uncharted territories. This need sparked the first major evolution in the surveyor's toolkit, a bridge from ancient sighting methods to the instruments that would define the modern age. The breakthrough came with the emergence of simple yet transformative devices like the cross staff and its more sophisticated cousin, the Jacob's staff. At its heart, the cross staff was a study in elegant geometry. Picture a long main staff like a walking stick with a shorter crosspiece that could slide back and forth along its length. A surveyor or navigator would hold the end of the main staff to his eye, then slide the crosspiece until its top and bottom edges seemed to touch two distant points, perhaps the horizon and a star, or two landmarks on a shoreline. By reading a scale marked on the main staff, he could calculate the angle between those points. This was angular measurement made portable and, crucially, quantifiable. It took the principle of similar triangles used for millennia on the ground and mounted it on a handheld frame. For a ship's captain trying to determine his latitude at sea, the cross staff was revolutionary. By measuring the angle between the horizon and the sun at noon, he could consult astronomical tables and know how far north or south he had traveled. On land, a surveyor mapping a coastline could use it to take bearings on headlands and islands, building up a chart from a network of intersecting angles rather than relying on impossible direct measurements across water. The Jacob's staff refined this idea further. Often longer and more stable, it sometimes featured multiple crosspieces or vanes for different kinds of observations, and it could be planted in the ground for steadier use during land surveys. These instruments did not invent a new principle, they optimized an ancient one. They gave the human eye a physical scaffold, turning an intuitive alignment into a number that could be recorded, shared, and used in calculation. This shift from qualitative to quantitative was profound. Where a master builder once knew a line was true because it felt right, now a navigator could state his position was a specific number of degrees north because his instrument told him so. It was the beginning of data-driven exploration. The cross staff and Jacob's staff represented a crucial middle step. They retained the direct, visual connection of the Dioptra, where the surveyor still peered along a sighting edge, but they simplified its form and broadened its use. They were the workhorses of the age of discovery, carried on caravels across oceans and in the saddlebags of cartographers charting new continents. By standardizing the act of measuring angles, they laid the essential groundwork for the next great leap, an instrument that would combine a perfect circle, a telescopic sight, and unparalleled precision, setting the stage for the theodolite and the world we measure today. This entire system functioned like a living organism where no single part could succeed alone. The true genius of ancient precision lay not in a miraculous invention, but in how these simple, reliable elements were woven into an unbreakable chain of verification. A knotted rope could define a right angle, but only the check of equal diagonals could prove it was true. The Groma's plumb lines could cite a straight path for a road, but only the disciplined process of ranging and the permanent milestone could carry that line across 50 miles of hills and valleys. The stars gave an eternal north, but only a water-filled trench could translate that celestial alignment into a foundation flat enough to receive it. Each method covered the weakness of another. The rope was portable but susceptible to stretch, so it was checked against the immutable standard of the royal cubit rod. The human eye could be deceived by a shimmering horizon, so it was disciplined by the fixed geometry of a 3-4-5 triangle. This was a culture of engineering that trusted nature's constant water-finding level, shadows tracing the sun's arc, stars circling the pole, more than any human-made device. Those constants became the silent partners in every project, the unchanging benchmarks against which all temporary materials and fallible senses were measured. Practical mathematics provided the language to speak across these domains, turning the observation of a star's transit into a number, and that number into a length of chord, and that chord into the side of a pyramid. But even this intellectual framework was inert without the final, human component, the skilled laborer whose hands had been calibrated by years of apprenticeship. He knew how to tension a rope just so, how to read the stilling surface of water in a windy trench, how to adjust a stone by a hair's breadth because the line of shadow told him to. The system was repeatable precisely because it was distributed. It did not rely on one genius with a secret. It relied on a master plan, standardized units, a hierarchy of oversight, and a shared toolkit of natural principles that any dedicated apprentice could learn. This is why a Roman engineer in Britain could build a road to the same specification as one in Syria. The culture itself was the tool, the stones that fit together without mortar, the roads that run straight for miles, the aqueducts that climbed invisible gradients. These are not separate mysteries. They are different expressions of the same integrated philosophy, a testament to what human societies can achieve when they build a complete and self-correcting conversation between the mind, the hand, and the unwavering laws of the natural world. This intricate system reveals a profound truth about the ancient world. Their precision was not born from secret technology, but from a deep, applied understanding of the universe itself. They saw geometry in the stars and physics in a still pool of water, then devised robust, elegant tools to harness those principles. The real marvel was not the rope or the Groma, but the disciplined human practice that turned observation into enduring stone. This redefines our view of their capability, shifting focus from the mystery of their materials to the mastery of their minds. It was an intellectual achievement of the highest order, built on patience, observation, and a relentless drive to communicate exact ideas across time and space. The legacy of these methods is woven into the very fabric of our modern world. The theodolite on a construction site, the satellite fixing a position, even the blueprint on an architect's screen, all are direct descendants of that ancient conversation between human ingenuity and natural law. The next time you walk a straight city street, stand in a centuries-old cathedral, or marvel at the line of an old stone wall, you are witnessing the quiet echo of that ancient precision. It invites us to look at the historical sites around us not as ruins of a lost past, but as permanent records of a brilliant, practical intelligence, waiting to be read with new eyes.